All right, I think we're live. Can everyone hear me all right? I'll give everything a moment to load in. Okay, cool. Sounds like things are working. All right, so welcome to the stream, everyone. Earlier today, the Infinity 2021 contest happened on CodeChef. It was an external rated contest for Div 2 and Div 3, but there were cash prizes for the combined ranks, or for the combined rank list between Div 1 and 2. So I was second in Div 1 and overall. Obviously, you can't really expect to beat Tourist too much of the time. Tourist, if you are watching this, please leave some contests for the rest of us. I would very much appreciate it. But yeah, so the plan for today is just to go through all the problems, talk through my solutions and my thought process, and answer any questions you all have. So I think we'll go ahead and jump right in. And I'm just going to start with the two Div 3 only problems. I think both of those will go pretty quickly. And then we'll move on to the problems from Divs 1 and 2. Okay, so starting with the first problem. We have a total of n players competing in the Squid Game, and when player I is eliminated, AI money is added to the prize pool, and we have to find the maximum possible value of the prize pool. Okay, so I'm actually going to get my notebook and draw this out. Okay, so first thing let's think about is what happens if player I wins? How much money will they receive? Well, all the other players are going to be eliminated, and so the amount of money player I will receive is the sum over all players other than I of their winnings, and we can write this as the sum over all j aside not equal to I of aj. Or perhaps more simply as the sum over all I of AI. Actually, I'm going to use j here just to prevent any confusion. Sum over all j of aj minus AI. And this summation is constant with respect to I, and so we just want to find if we want to find the maximum value of this expression, all we have to do is find the minimum value of AI and then subtract it from the total. And so the solution here is just to add up all the values of AI except for the minimum and then print out the result. And so I'll show you my code. Pretty straightforward. I just sort the array and then I skip a of 0 when I'm adding them up, and that means I'm skipping the smallest element and adding up all the rest, and then I print that out as the answer. Okay. Pretty quick. So next problem. I think the statement here is somewhat annoyingly confusing. But ultimately, what this problem is asking us to do is just we're just pretty much directly told to count the number of elements greater than k in the given array of n elements. And so it's a pretty straightforward implementation problem. We read in n and k, and then I'm just going to read in all the elements. I don't even need to store them in an array. I'm just going to read them in, and if they're greater than k, then I'll increment the answer, and then I'll print out the answer. So nothing too fancy here. Pretty straightforward. I think understanding what the problem is saying, getting through the flavor text is the really only non-trivial part of this one. Okay, so let's move on to the problems from the Div 1 and 2 round, most of which were also shared with Div 3. So, starting with marbles. Okay, so we're given two strings S and P of length n. And what we're going to do first is we're going to replace every occurrence of a question mark in either of the two strings with a character of our choice. And we have to use the same character for every question mark. And afterwards, we're allowed to perform two operations on P. We can change a vowel to a consonant, or we can change a consonant to a vowel. And we have to find the minimum number of operations it takes to convert the string P into the string S. Okay, so for a problem like this, I think a lot of the time it can be helpful to solve a simpler version of the problem before moving on to the full task. And so in this case, the first thing you can think about is, what would we do if there were no question marks? What would we do if we already knew the strings S and P, and we didn't have to do this first step of replacing the question mark? Well, the first thing you should notice is all of the letters are independent. So like changing the first letter of P isn't going to like mess with the second letter of S and P. And so we just need to find the cost to change the first letter of P into the first letter of S, plus the cost to find the second letter, or to turn the second letter of P into the second letter of S, plus the cost to change the third letter of P into the third letter of S, and so on. And so ultimately we need to add up the cost of converting P of I to S of I over all I. So then how do we find this cost? So there are a few cases here. First, if P of I is equal to S of I, then we don't need to make any operations because the two characters are the same. Second, if one of P of I and S of I is a vowel and the other is a consonant, then we're going to need one operation. Because if P is a vowel and S is a consonant, then we're allowed to just use this first kind of operation to change P into S. And likewise, if P is a consonant and S is a vowel, then we can use this operation. On the other hand, if both are vowels or both are consonants, then we're going to need two operations. Because we can't change P directly into S if P and S are both vowels or if they're both consonants. But what we can do is, for example, if P of I is B and S of I is C, for example, then we can change B into A using an operation of the second type, and then A into C using an operation of the first type. And so it is possible to do this in two operations. And some comments that this question is similar to one of the problems from Facebook Hacker Cup earlier this year. I think I vaguely remember this. Yeah, that sounds right. But anyway, so we can just add up these values in order to get our answer for this subproblem. And I'll go ahead and show you my implementation just for this small part of the problem. What I do is I start with this array, with this Boolean array vowel that I just initialized to indicate whether a given character is a vowel. And so later on I pre-compute this so that the values corresponding to 0, which is A, 4, which is E, or similarly the positions of I, O, and U are all true in this array and everything else is false. And so from here, to find the cost of, I just say getting from S to T, I say, okay, if S is not equal to T, then that's going to be a cost 1. And moreover, if they're not equal and both are vowels or both are consonants, then we have to increase the cost again because this case has cost 2. Okay. So that's how we can solve the problem if there are no question marks. And so now what we have to figure out is how to solve the problems without question marks. With question marks. And the key idea here is that there really aren't that many things we can do with the question marks. We can just pick one character and then change all the question marks to that character, but there are only 26 choices. And this little subproblem solution runs in O of n time. And so running this 26 times is completely feasible. And so what we can do is we can just try every possible letter to use as a replacement for the question marks. And then for each of those letters, we can just construct the resulting strings S and P, find their costs, and then we can just find the minimum among those costs. And this brute force works in time because n is only up to 10 to the 5th, and so 26n, which is about 2.6 million, is definitely feasible to run in time. So I'll show you my code. What I do is I iterate over I from 1 to 26, which is the character we're using to replace it. Then, first I build, A and B are going to be the new values of S and P. And then for everything in S, if it's a question mark, then I add in the current character that we're using. Otherwise, I just add the letter from S. And then I use a similar thing to build B. And then I set the answer to the minimum of itself, and the cost from A to B. Yeah, and so that is the solution here. So Soham, I guess there are probably other ways you could do. Sorry, I should repeat the question. So Soham asks if there are any alternatives to brute force here. So let's see. Yeah, so so if you wanted to, I think what you could do is you could build a frequency array, essentially storing like the number of times, for example, question mark to G happens, question mark to C, question mark to K, just storing the amount of times a question mark appears next to each of those things, and then based on that array, you could use it to, or you could count or you could find essentially the cheapest cost of question marks, and then it would take then it might run slightly faster, because then you would only need to iterate through the string once rather than 26 times. However, it would be a lot more of a pain to implement, and the asymptotic complexity actually would not be any better, because here 26 times n is still O of n, and so there's no way to do this problem faster than O of n. It would be possible to cut down on the constant factor, but that also would require more implementation. And in the context of a programming contest, our goal is generally just to implement the simplest solution that works. So yeah, and Oli says they did it using the frequency array. And so yeah, so using this frequency array idea would work, but it would just be a little bit more annoying to code, I think. Maybe not that much more annoying, but a little bit. Sorry, my chair is so squeaky, by the way. I'm not sure if that's coming through on the mic. Anyway, so that's marbles. So let's see. Why don't we move on to the next problem? A little hard to choose the order here because the difficulty site or ordering differs significantly from div 1 to div 2. I don't really have any idea why so many people solve this hopscotch problem in div 1. I'm wondering if it had appeared somewhere before, because I definitely don't think it's the next easiest problem on the contest. So I'm just going to do Dalgona next. Okay. So what we have to do is find an array A with n elements such that the sum of all of these elements is a perfect square. And moreover, this array has to have, or can't have too many distinct values. Okay, so I think there are lots of solutions to this problem, and so you guys might have other ideas than what I did, but I'll just describe one of the solutions real quick. So generally, when we're working on very open-ended constructive problems like this one, where it's maybe not particularly obvious just from this condition what to do, and where it looks like there could maybe be a whole lot of different solutions that work, a lot of the time it can be really helpful to impose some additional constraint on the solution we're trying to construct, so that we can solve the problem a little bit more systematically. And here, after trying a couple of things, what I decided to do is I just said, let's say that x is the first number in our output array. And then we're going to try to build an array such that the sum of ai squared is equal to x plus 1 squared. And the reason this is helpful is because, let's say that, and so the reason this is helpful is that let's say that the sum of ai squared, or let's say that a1 is x, and then we're going to say that the sum of a2 squared plus a3 squared plus all the way up to an squared, I'm just going to call this s. And then we need to have x squared plus s equals x plus 1 squared. And simplifying, we have x squared plus x equals x squared plus 2x plus 1, which gives s is equal to 2x plus 1. And so now, we can, if we solve this equation for x, we get x is equal to s minus 1 over 2. And so, if we can find, and so we know that x has to be a positive integer, which means that s here is going to have to be an odd integer greater than 3. Or sorry, at least 3. Since this is going to be at least 2, and then so 2 plus 1 is at least 3. And so here now we just need to find n minus 1 elements that sum to, or whose squares sum to an odd integer that's at least 3. So and then we can just construct the value of x as s minus 1 over 2. Now this is nice because it turns out this is a much easier problem. First of all, let's say that n is even. If n is even, then n minus 1 is odd, and so we can just take n minus 1 ones. Because then s is going to be n minus 1, which is odd, and so then s minus 1 will be n minus 2, which is even. So s minus 2 over 2 will be an integer, so it'll be a valid choice for x. The one edge case here is that if n is 2, then when we take n minus 1 ones, that'll just be 1, 1, and then s will be 1, which would give x equals 0. But here the arrays have to be, the values in the array have to be positive. And so we need to come up with a different solution for n equals 2. And for n equals 2, and so what I did here is I just said, okay, let's just take our array to be 3, 4, because 3 squared plus 4 squared is 9 plus 16, which is 25. So 3 squared plus 4 squared is equal to 5 squared. Now, if n is odd, we can't do the same thing, because if we take n minus 1 ones, then we'll have an even sum, and we need our elements to sum to an odd number. So let's just do the next best thing. Let's take 1, 4, and n minus 2 ones. So that gives s equal to 4 plus n minus 2, which is n minus 2, and since n plus 2, this should read. And since n is odd, n plus 2 will also be odd, and so this is a valid choice. And so here the edge case is if n equals 1, then we can just output any array, because the sum of ai squared will just be ai squared. Or sorry, will just be a1 squared, which we know is a perfect square. So we can just use any array. So I just used 1. And so I'll show you my code. It pretty much goes through these cases straightforwardly. So first I handle the 1 case, I just output a 1. For the 2 case, I output a 3 and a 4. Now I use this weird map setup, and the reason I do that is so that I don't need to be careful to handle the case, or is because like the output format is a little strange. It has us just output the frequency array, and I didn't want to have to worry about the case where our element x is also the one of the ones or the twos that we're adding down here to create s. And so instead I just build the frequency array in this map A, and then I output the frequency array from the map. And so if n is odd, then I use n minus 2 ones, and then 1, 2, and then afterwards I just have a n plus 1 over 2, which since s is going, and because s is going to be equal to n plus 2. Okay, and so if n is even, then I just use n minus 1 ones, and then with s is equal to n minus 1, so then x is equal to n minus 2 over 2, which is n over 2 minus 1, and that's how I get this line. And so from here, I can just print out the answer. So yeah, again, there may be other ways to do it. Joshua in the comments says that they did it with the Chicken McNugget theorem, which is something that I was thinking about, but I felt like the constraint that we needed to have exactly n elements in the array would make that a bit annoying to do. And so this approach, and so here, I think there may be other ways you could do this rather than trying to like start with x and then create x plus 1 squared. But this at least worked pretty nicely to me, and it helped me to be able to think about this more systematically by imposing this additional constraint. Okay, so next problem I'm going to do Tug of War. Okay, so we have we have 2 teams. The match proceeds in a series of rounds where the frontmost player from each team will play. Whichever player has the greater strength will stay in and the other will be eliminated. And if they both have the same strength, then both players will be eliminated. And we have to find, and so we're given the strength array of the opposing team, and we have to find the, and we're given the strength array of our team, and the opposing team's order of in which they'll play is fixed. And we have to find the lexicographically minimal ordering of our team that will allow us to win the game. Okay, so the first thing that you should notice here is that if our team has a player stronger than any player on the other team, then we are guaranteed to win because that player can just defeat the entire other team on their own. And so if that happens, then we can just sort our array and print out the result because if any permutation of our array will work, then we might as well just print out the lexicographically minimal one. And on the other hand, if their team has a player stronger than our entire team, then they will always win and there's nothing we can do about it. And so the tricky case that we're going to have to think more about occurs when the best players on our two teams have the same strength. And in this case, they're going to eliminate each other. And so that means we can't put our best player at the very back, because if after they're eliminated, we won't have anyone else, so we'll lose. And so we need to have a backup player afterwards so that when the best players eliminate each other, we won't be left with no player standing. And so an example of this is the second sample test case, where the opponent's team has 2, 4, 7, and we have 2, 3, 7. What we're going to need to do is we're going to leave the 3 behind the 7, and we're going to do 2, 7, 3. So that then we have 2, 4, 7. In the first game, the 2s eliminate each other. Then our 7 eliminates their 4. And then the 7s eliminate each other. But then because we stuck that 3 in the back, we still have a player left, and so we win. Now, the other thing to think about is, okay, if we need to stick someone behind our best player, who should that backup player be? Well, in order to make the permutation lexicographically minimal, we want to keep the weakest players at the front. So what we're going to do is we're just going to move the second strongest player to the back. And so here we're going to keep the 2 in the front, and then we'll put the 3 behind the 7. But then the second strongest player may still have to defeat some of the remaining players after the strongest player is eliminated. And an example of this is in the second sample case. If we have 2, 7, 4 versus 2, 7, 3, the 2s will eliminate each other, and then the 7s will eliminate each other. And so our strongest player is gone, but then our backup still needs to play and still needs to defeat this 4 that the other team has left behind. And again, if the second strongest player loses in this process, then we can't win. So this third test case is an example of this. We can't win because after we lose our set, we're going to have to give up our 7 in order to beat their 7. But then we're going to lose, our 3 is going to lose to their 4. Otherwise, the second strongest player might just be able to beat some of their players, but they may draw, in which case we're going to need to pull out the third strongest player as a backup. And so an example of this, I'll just come up with one right now. Let's say that we have 2, 4, 7, 5, and we were given let's say 2, 3, 6, 7. Then the best we can do is 2, 7, 6, 3 because the 2s will eliminate each other. 7 will beat 4. 7s will eliminate each other. Actually, hold on, sorry, this should be a 6. And then the 6s will eliminate each other, and now we need to have our third strongest player waiting in the back so that we can still win the game. And so ultimately we can just repeat this process until we reach the end of the opponent's order. We can try and put our strongest players in the back until we've defeated all of the opponent's players, and then whichever players we don't need to have in the back, we can just sort and place them at the front. And another way you can think about what I'm doing is that I'm simulating the match if we sort our players in descending order. And then I take whichever players never get to the front of the line by the end of the match, and I just put them in the front of the line because if those players lose, it doesn't matter because we can win the game with only the remaining players. So I'll show you my code, which I think also may make this idea a little clearer. So I read in the data, and then this variable p represents the current player on our team that we're working with. So initially, P is m minus 1 because I've sorted our teammates, and so m minus 1 represents the strongest one. Then, if the best player we have left loses, then we can't win because there's no way we can beat this player. So we say print no. Otherwise, if they draw, then we decrement the current player. We move on to the next player because our current one is eliminated. And if P becomes less than 0, then we're out of players, and so we have to print no. And otherwise, we can print yes. And we can print whichever players are less than P, whichever ones didn't have to play, in descending order, and then the ones that did have to play in descending order, decreasing order. Yeah, so this is a bit of a tricky one, so I'm happy to answer questions if you all have any. But that was the solution approach I used. Coding Master says congrats on second place and for getting a prize. Thank you very much. Okay. So now I think I'll look at this Hopscotch problem. I found the phrasing of this problem pretty confusing. I think the second constraint makes it look like if A of I is equal to J, then player I will choose the mannequin that the jth player takes. So I'm going to rephrase this problem to try and make it a little bit more clear. So we're given an array A where if A of I is equal to J, then player I has already chosen mannequin J. And if A of I equals 0, then player I has not yet chosen a mannequin and needs to be assigned to a mannequin other than mannequin I. And we have to figure out, we have to count the ways to assign the players who haven't yet chosen mannequins to the available mannequin, such that if A of I equals 0, then player I does not get mannequin I. So yeah, this is a bit of a tricky problem. I think the first thing I want to talk about here is what the constraints tell us about the solution we're going to employ. So here we have t up to 1,000 and n up to 1,000, but there's no limit on the sum of n. And this looks a little strange because if our solution ran an O of n per test case, then the maximum value of n could be bigger, because t times n is only 10 to the 6th. We could have n up to 10 to the 5th, or I guess then reading in the input would be hard, but we could have a larger n, and we'd still be able to run in time if our solution was O of n per test case. But if we tried to use an O of n squared solution for each test case, n squared times t would be 10 to the 6 times 10 to the 3, which is 10 to the 9, which is too big. We can't do, or we wouldn't be fast enough. And so what these limits should suggest is that we're going to do some pre-computation in O of n squared time, and then answer each test case faster than that, maybe in O of n, since we're going to need O of n time to read the input anyway. Kron says I wasn't able to understand the question. Can you explain it again? Yeah, let me try and explain this again. So we're trying to assign players 1 through n to mannequins 1 through n, and we know that, and some of the players have already chosen mannequins. We've already assigned them for players who, and that happens if A of I is not equal to 0. And so in the second test case, for example, player 1 has chosen mannequin 3, player 2 has chosen mannequin 6, and player 3 has chosen mannequin 1. But then there's some players who haven't chosen mannequins, and so in this case, players 4, 5, and 6 have not chosen yet. And what we have to do is we have to assign the players who haven't chosen yet, so players 4, 5, and 6, to the available mannequins, which in this case are just whichever ones aren't already chosen, so 2, 4, and 5. And we have to do that so that none of these players who haven't chosen yet get their own mannequin. So, okay. So again, the goal here is we're going to do O of n squared pre-computation, and then answer each test case faster than that, maybe in O of n time. Deadly Coder asked in the chat if this problem has anything to do with derangements, and that's right. And so, this problem may be a little familiar to you, and in fact, if you haven't heard of derangements, then I would recommend looking them up and learning some about them before continuing with this problem because I think it's a helpful concept to understand. For people who aren't aware, derangement is a permutation P in which P of I is not equal to I for all I. And so here, what we're trying to do here is pretty similar. We're trying to make sure that A of I, or that like the mannequin chosen by players who aren't yet decided, is not equal to I for those players. But in fact, there's a dynamic programming way to calculate the number of derangements of an array, and we're going to do something very similar here. So what I'm going to do is I'm going to let dp of I of j be the number of ways to assign I undecided players to I mannequins, such that among these I players, j of their mannequins have already been taken. And so just to illustrate what that means for this second test case, here we have 3 undecided players, so I is 3, but then among them, one of their mannequins has already been taken, mannequin 6 has been taken, and then 4 and 5 have not. So the answer to sample test case 2 is dp of 3 of 1. And so our base case here is dp of 0 is equal to 1, and that's because if we have no undecided players and no mannequins, then we can just use the empty assignment. That's the only way. And so now let's look at our transitions. So our goal is we're going to build dp of I of j based on earlier values of the dp array. And so we're going to break into 2 cases here. So first, let's say that j is equal to 0, i.e. like for all of the mannequins left, or for all of the players left, none of their mannequins have been taken. So we're going to look at the number of ways to assign the first player to a mannequin. Well, there are I players left, so there are I mannequins remaining, but player I cannot take mannequin I, and so they can only choose from I minus 1 of these mannequins. And from here afterwards, this player must choose someone else's mannequin, which means that one of the remaining players will have their mannequin taken, and so j is going to increase by 1. And so we have 1 fewer player, but we have 1 more player whose mannequin has already been taken, and so this gives us I minus ways to transition from dp of I minus 1 j plus 1. Now, let's say that j is positive. So what we're going to do is we're going to assign the first player whose mannequin was already taken to a mannequin. And the reason we can do this is if j is greater than 0, then one of our unmatched players already has had their mannequin taken. And so we can just assign them to some other mannequin. And so here there are 2 subcases. So the first thing we can do is assign this player to a mannequin corresponding to someone who hasn't chosen yet. And since there are I players left, with I players left and j of their mannequins are taken, there are I minus j remaining mannequins corresponding to players who haven't chosen yet. And so this means that we can add I minus j times dp of I minus 1j to dp of I of j. And the reason j stays the same is that the current player has already had their mannequin chosen, and so now we're losing 1 player whose mannequin has already been taken because we're assigning one of them. But then if we're taking a mannequin corresponding to a player who hasn't chosen yet, that's going to increase j by 1 because now there's an additional player who hasn't chosen yet but whose mannequin is already taken. And so the second case is to assign this player to a mannequin corresponding to someone who already chose. And so here, there were I minus j mannequins taken, or that were available in the other step, and so the remaining mannequins, if there are I left in total, that means that there are j mannequins we can choose this way. And so here, dp of I of j will increase by j times dp of I minus 1, of j minus 1, because here now we're again we're losing a player whose mannequin has already been taken because we're assigning them to one of the mannequins, but then we're not but then now we're just they're choosing a mannequin corresponding to a player who has already made their selection, and so j is going to decrease by 1. Fine, and so this is how we can pre-compute the DP. Now, for each test case, what we can do is we can just count the number of players who haven't chosen yet, so here that would be 3, and then count the number of their mannequins that are available, and just print out the corresponding entry of our DP table. And so I'll show you my code real quick. I think I called this F. So first, to compute the DP, I start with just this base case 0, 0 is 1. Then I implement it like pretty much exactly like I said here. If j is 0, then I add I minus 1 times DP of I minus 1, j plus 1. And otherwise, I add the I just add in the 2 cases I just discussed. And then I just print out the solution. I use this bool array to store which mannequins are left available. And then CNT stores the number of values of a of I that are equal to 0, so the number of players who haven't decided. And then I use cchoose to count the number of undecided players whose mannequins are already taken. And then I just print out the corresponding entry of DP. Something I want to highlight is I actually think that their answer for this first sample test case is wrong. Here they say that there are 5 so there are 5 players, all have chosen their own mannequins, and so then they say that with no undecided player, there's no way to assign the undecided players to mannequins. I don't think this is correct. I think with no, or at least I don't think it's a good convention to use. With no players who haven't chosen yet, there's just one way to match all of them, which is just the empty assignment. And indeed, that's the value of DP of 0 that makes sense when you're computing the rest of the table. Because of this, because they decided to call this 0, I had to just go back and change DP of 0 to 0, just to 0 retroactively at the end of my code. So, I think that was a little silly, but oh well. Okay, so how many problems do we have left? We got 3 problems left. So let's keep going with msum. Okay. So this is a tricky problem involving quite a bit of casework. We're given an array of n elements, and we're allowed to just subtract any element from any other element. And CubeFreak says we can do the problem in linear time using principle of inclusion-exclusion. Yeah, very nice. Okay. So, and what we have to do is we have to minimize the sum of the absolute values of the elements in this array. Okay. So, there are a couple of observations to make, and then we're just going to have to do some casework. So the first observation is that the GCD of the numbers is never going to change. I.e., like for example, this is the 4th test case. The numbers are 0, 2, -2, and 6. The GCD, the greatest common divisor of these numbers, is 2, and indeed all of the numbers are always going to remain visible by 2. Or divisible by 2, sorry. Because like if we take a of I minus a of j, and ai and aj are both divisible by our GCD, which I'm going to call g, then ai minus aj will be divisible by g. I.e., if g is equal to GCD of a1, a2 up to an, then every element will always be divisible by g. Okay. So now what I'm going to do is I'm going to start with the simpler case where all of our numbers are positive, and the case where all the numbers are negative is the same. And then I'm going to extend that to the case where we have some positive numbers and some negative numbers. So there are a few observations we need to make. All right. So I'm going to write all positive. So first observation, the answer is never 0. And the reason is that if we have n-1 zeros and 1 non-zero number, then then any operation we perform will either, if we use ai as one of these zeros, then it might make it into a non-zero number, but if we perform an operation on the non-zero number, then the only thing we can subtract out is one of the other elements of the array, which is 0. And so what that means is it's never possible to just delete the entire array. We're always going to have one element left. The second observation is if we can create G, if we can get G to appear in the array, then the answer will be G. And the reason is that we can just subtract G from every other element of the array until all elements are 0. And the reason this works is because since G is the GCD of the array, everything will be a multiple of G. And so an example of this is in our first sample test case. The GCD of 4 and 1 is 4, and we constructed 1, and so we can just subtract 1 from 4 times, and then 4 becomes 0, and then we're just left with 1. And in this third test case is actually another example. The GCD is 10, and so we have 10. We can just subtract 1, 10 from all of the others, and then we're left with 1, 10, and 4 zeros. And we can't create 0, and our elements are always going to be multiples of G. So creating G is just the best we can do. And so if we can create G, then that's our best answer is going to be G. Now, it turns out we can always create G. And the reason this is true is it's kind of similar to the Euclidean algorithm, actually. What we can do is we can create, to create the GCD of 2 elements, repeatedly subtract the smaller one from the larger one, and then this is the Euclidean algorithm. It's going to get us the GCD of those 2 elements, and then we can just repeatedly take the GCD of the current GCD and the next element of A in order to get the GCD of the whole array. So thus, when the elements of A are all positive, the answer is always G. And the same logic works when A is negative. When A is negative, we're just going to try and create negative G. And so the hard case comes when some elements of A are positive and some are negative. So the first thing, let's talk about what we can do in this case. The first thing to notice is that we can never make all the numbers positive or all negative. And the reason for this is that, for example, if we only have one positive number and all the other numbers are negative, then all we can do is subtract out a negative number, which will just make it more positive. So we're never going to be able to make all the numbers positive or all of them negative. And so that means we'll always have at least one positive number and at least one negative number. So the best we can do then, since everything is going to be a multiple of G, we're going to want to get G and negative G, and then we're going to have an answer of 2G. Now, this is usually possible, but it's not always possible. And the edge case occurs when n is equal to 2. So, for example, let's say that our array is 2 and negative 3, which gives G is equal to 1, because the GCD of 2 and negative 3 is 1. Then, if we subtract negative 3 from 2, then 2 is just going to be bigger. If we subtract 2 from negative 3 is just going to be smaller. So we can't actually bring either of these 2 values from 1. All we can do is just bring them closer to, or all we can do is just bring them further away from 0, which isn't going to help us. So what we should do is, if n equals 2, keep the array the way it is and output the absolute value of A1 plus A2, or plus the absolute value of A2. Now, if n is greater than 2, then what I'm going to claim is that we can always create a G and a negative G. And the algorithm to do so is, first, create the GCD of the positive elements of A, and we can do this using the Euclidean algorithm described up here. Then create the GCD of the negative elements of A. And then the third thing we're going to do is we're going to subtract, or is we're going just to take some third element and let's see, what can we do here? Sorry. And take some third element and then just subtract out the GCD of the positive elements until it's negative and it's been subtracted at least once. Actually, wait, no, hold on. This is okay, so I'm going to assume here that there are two positive numbers, and that if there are two negative numbers, it works the same way. So then what I'm going to do is take a second positive number and turn it into -1 times the GCD of the positive numbers. And remember that the way we can do this is because the second positive number is going to be a multiple of this GCD, so we can just subtract out this GCD until this number is 0, and then subtract it out one more time. And then finally, create the GCD of -1 times the GCD of the positives and the GCD of the negatives. And then this is going to equal negative G. And then finally, subtract negative G from the GCD of the negative elements until we get positive G. And so that's how we can construct G and negative G. All of the claims here is going to take some time, and so I'm not going to go through it in more detail. If you have questions, I'm happy to answer them either now or in the comments on the stream afterwards. But the point is that when n is at least 3 in this case, the answer is always going to be 2 times the GCD. And so the code turns out to be very short. I just take the GCD of the entire array, and then I sort it, and if the smallest element is positive or the largest element is negative, then I print out the GCD. Otherwise, if n is 2, then I print out the sum of the absolute values. And otherwise, I print out twice the GCD. Okay. So now let's look at this second to last problem, which I actually think is easier than this one. Okay, so escape plan. Here, we're given a tree with vertices that each contain some value, and we get to change some of these values to 0. So we get to change AB to 0 with some V, and our goal is to make sure that the bitwise OR on the path from the root to each vertex remains non-zero. And under that constraint, we want to minimize the sum of these ORs. Okay, so the first observation we're going to make is that there should be only one non-zero value on the path to each leaf. And the proof of this is that if there are 2 non-zero values, we can turn whichever one is deeper in the tree to 0. And when that happens, the corresponding leaf is still going to have a non-zero XOR because the less deep one will still be non-zero. But now we're going to be turning off some bits, so the bitwise OR will be smaller. So then we'll still have non-zero ORs in the leaves, but those ORs will be smaller, or maybe the same. But it's never any better to turn on or to keep some extra values of A, such that there are 2 values of A corresponding to the same leaf. So what we're going to do here is we're going to do some tree DP. And we're just going to let dp of v be the answer corresponding to the subtree with root v. And there are 2 kinds of transitions here. So first of all, the base case for leaf v, the p of v is just going to equal a of v because we just got to keep a of v non-zero if all we have is a leaf. And so then there are two kinds of transitions. The first kind is we can take the p of v to be a of v times the number of leaves in v's subtree. And the reason we can do this is this corresponds to keeping a of v positive, but then setting all the other a's in the subtree of v to 0. Then the bitwise OR on the path to any leaf is just going to be a of v, and so we can multiply a of v by the number of leaves in v's subtree. Alternatively, we can say dp of v is equal to the sum of dp of a over all children a of v. And this corresponds to setting a sub v to 0, and then but then keeping all of the values of a that we've set earlier. Now, the one catch here is we have to deal with cases where a of v is 0, because if a of v is already 0, then, for example, this first kind of transition doesn't work, because if we set all of the descendants to 0, then we'll end up with some values with no XOR. And so this creates two additional constraints. The first is if a of v is 0, we can't use the first kind of transition. And that's because, and so if we turn everything else in v's subtree to 0, then v's leaves would have bitwise ORs of 0. And then the second constraint is if dp of a doesn't exist for some child a of v, then we can't use the second kind of transition. And this might be an issue if, for example, all the values of a in some subtree are 0 just as they're given to us. Then we're going to need to create or to keep a non-zero value so that the leaves in that subtree will have non-zero OR. And once we deal with those restrictions, though, we're all finished, and so we can go ahead and start implementing. So all through my code, most of it happens in this DFS function. I use this OK variable to represent whether or not the value or the DP value exists. So the first thing I do is I just set dp of v to be the sum of dp of a over all over all children a, and this corresponds to the second transition. I use CNT and I use OK to represent whether dp of v exists, and I use CNT to represent the number of leaves in v's subtree. Now, if there's any child of v for which dp doesn't exist, for which OK of a is false, then I'm just going to reset dp of v to 1 or to 10 to the 18 just to sort of undo this second kind of transition. Meanwhile, if I haven't found any children of v, then that means v is a leaf. So I'm going to say, okay, it has one leaf in its subtree, which is itself. And finally, what I'm going to do is if a of v is positive, that is, if we're allowed to do the first kind of transition, then I'll just do that. I'll just attempt the first kind of transition and then return the result. And then our answer is just dp of 0, the dp corresponding to the whole tree. All right, so that's escape plan. We're moving on to the very last problem. So we're given a tree consisting of n nodes. It's rooted at node 1. Each node has a value a sub I, and we also have a set of special edges s. So we have to answer a bunch of queries, and two of the types of queries are pretty simple. We just have to add or remove an edge from s. But the first kind of query is a little bit more complicated. We consider the subtree of U, and we have to remove exactly k-1 edges outside of S in order to maximize the sum of ZV, where ZV is the number of edges removed on the path from U to V plus 1, times AV, where A is an array that's given to us. And so what I'm going to do is first I'm just going to maintain the set of non-special edges, since those are the ones we're allowed to use in queries of type 1. And so in short, when type 1 queries occur, we have to mark, I'm just going to say we're marking the removed edges. We're going to mark k-1 edges in the subtree rooted at U, And then we have to, or in order to maximize the sum of AV times the number of marked edges on the path to V over all V in the subtree of U. So I think the most important observation here is that we can change this summation to be a sum over the marked edges rather than a sum over the vertices in the subtree. So let's say that we're going to consider an edge from A to B, where A is the parent of B. Then marking this edge adds 1 to ZV for all descendants V of B, because this edge is going to be on the path to B, it's going to be on the path to B's children, it's going to be on the path to B's children's children, and so on. So let's let value of V be the sum of A of A over all descendants. Actually, I'm going to use D here just to use a new variable name, over all descendants D of V. Then when we mark the edge whose child node is V, we add val of V to the answer. And so we want to maximize the sum of val of V over chosen edges V. And so now all we need to do is we need to find the k-1 largest values of val of V within a given subtree. And it turns out that this is a pretty standard problem using a segment tree on the preorder traversal. Very common technique in tree problems. I encourage you to look it up if you aren't familiar with it. So what we're going to do is we're going to start by performing a preorder traversal of the tree. And this is really valuable because in any preorder traversal, subtrees of the original tree correspond to ranges in the traversal. And so now we've transformed our subtree queries into range queries on an array. And now we're going to use our favorite data structure for range queries on an array, which is a segment tree. So we're going to build a segment tree on the preorder traversal that will let us find the maximum val of V within a range and the position of that val of V. To answer queries, what we're going to do is we're going to start by pre-computing val of V for all V. Then to answer queries, all we need to do is just repeatedly find the greatest val of V within our subtree, then remove it from the segment tree. Then we'll add all the vals we use back to the segment tree when we're done. This is going to end up taking O of nk segment tree queries, I guess O of qk, sorry. So the complexity is O of qk log n, which is a little marginal, with n and q up to 10 to the 5th and k up to 30, but it might actually end up passing in about 1/7 of a second, so it turns out to be remarkably efficient in practice. Now, the one thing I haven't really talked about yet is how we're going to deal with the set of special edges, but it turns out that that's actually pretty easy, because we can just remove val of V from the segment tree while edge V is special, and then add it back when we make edge V non-special. So I'll show you my code. It's kind of long and complicated. So here's my segment tree. It's just going to store pairs of long longs where the first value is equal to val of V, and then the second value in each pair is equal to the position. And then, and it's just a maximum segment tree over those pairs. And so then I use DFS. This time in and time out correspond to the preorder traversal. P corresponds to parent. Pre is the prefix sums, which I use to deal with the fact that because we have to add 1 to Z of V for all of our vertices in the subtree, we have to find the sum of, or we have to add the sum of A over all vertices in our subtree to the answer. And so using these prefix sums lets me do that. So then I set the value of, I initialize val of V to just be A of V, but then I add val of A for all the children. And then from there, for each of the elements initially in our special set, I remove them from the seg tree, and I do that just by setting their corresponding position to be a really small value that we'll never want to choose. Then I handle our queries just by for k minus 1 times, I query the corresponding range, and if the query tells me there's no solution, I say, okay, this doesn't work. It's impossible. And otherwise, I just keep adding the value of each edge to the answer. And for queries 2 and 3, pretty simple. I just update to add and remove from the segment tree. So yeah, that is the contest. Overall, pretty fun round. I don't know, there were a couple of things that maybe could be improved. First of all, I think that the phrasing of this problem could be improved. First, just to make this second condition more clear, but also I think the answer to this first sample case should just be 1. And then I also think there's a pretty big gap that you can sort of see in the div2 and div3 rank lists between marbles and all of the remaining problems in the set. And so it might have been best to maybe switch up a few of the other problems to make them a little easier in order to make it, or so that there would be more to do for people who are kind of in that skill gap between those two problems. But overall, I thought it was a fun round. There were some nice problems. Appreciate the organizers putting it on. And yeah, I think that is all I have. So thank you all for watching. I'm looking forward to doing some more streams over the next couple of weeks. And I will see you all soon. Have a good one.